Hello and welcome to today's webinar presented by Deluval Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is Introduction to Time History Analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Cisco Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. Regarding the content over the next hour today, I do want to give a brief introduction to the dynamic analysis add-ons within our FEA program, RFEM 6. We will be taking a look at the natural vibration analyses of our structures utilizing the modal analysis add-on. And we'll also introduce external excitations over time utilizing our new time history analysis add-on in RFEM 6. We'll be working through a couple of examples. The first is going to be machine-induced vibrations with the structure shown over here on the right-hand side of the screen. And finally, a quick example at the end to showcase a blast analysis, also utilizing that time history analysis add-on. So for those of you not familiar with our program configuration, RFEM 6 is the base program that allows us to fully model the structure where we have access to the materials and cross sections from the various standards. We can load the structure and run a full static analysis. But when you need dynamic analysis capabilities, it will require one of the 4 add-ons listed here. The first is the modal analysis add-on. So this allows us to calculate the mode shapes of our structures and determine the natural frequencies, periods, and angular frequencies of the structure. So this is a prerequisite for the additional add-ons that you see listed here. The second is a response spectrum analysis. So this is a seismic analysis according to the ASCE 7, the NBC, and other international standards that we offer. We also have the recently released pushover analysis. This is a nonlinear analysis for seismic deformation behavior, and currently this is according to the N2 method. And finally, we have our linear time history analysis. So this is to introduce external excitations as a function of time. So today we'll be working in both the modal analysis add-ons as well as the time history analysis add-on. So to turn here to the features within the time history analysis, we certainly have improved the integration and the workflow in our new version RFEM 6. And when we compare this to RFEM 5, it was a little bit of a 2-part process, quite a bit different to open up the dialog box, then to define all of the dynamic time history analysis settings. Now you'll see in RFEM 6 a much more fluent workflow where we can better see that add-on integrated in the main program. We can combine user-defined or function time diagrams with nodal, member, surface, free, and generated loads. So the point being that we have the ability here to include many different load types in correlation with these time diagrams. We can also combine multiple independent excitation functions for one analysis. We'll see this with our first example today. We do offer the linear implicit newmark or the linear modal solvers. And it should be known that currently in the program that all nonlinear elements for a time history analysis are going to either be ignored or converted to linear elements. So for example, if you have failure in uplift for a support condition, this will simply be converted to a standard support for that dynamic analysis. Same concept with a nonlinear tension only member. Internally, this will automatically be converted to a truss element. We can consider structural damping with the Rayleigh damping coefficients or the Leer's damping values. And finally, when we do run our calculation, we'll see an output of the graphical results displayed, but also we can create what we call calculation diagrams. So we see a calculation diagram shown over here on the right-hand side, which just gives us a better idea of what's going on with the structure over that total time duration. We can In addition, display these results for each individual time step or as an envelope solution during the entire time period. And we'll work through most of these topics today with our examples. So we'll begin here with example number 1, where we are going to introduce these machine-induced vibrations with the steel industrial structure that you see here on this slide. We have 2 rotating machines, and you can see here where these machines are going to be placed. We have one at the upper level where this opening is on the right, and then at the first level here at the center, we'll place that second machine. So these machines are operating at 325 rotations per minute. The mass of the machine is 2,000 pounds, or converted to 62.16 slugs. The mass of the rotor is going to be 700 pounds, which converts to 21.76 slugs. And the rotor is going to be operating at an eccentricity of 0.75 inches. Therefore, we want to calculate the excitation frequency here. So we just simply take the 325 rotations per minute, we divide by 60 seconds, and we get a value of 5.42 hertz. So this is a really important number to remember and will come into play a little bit later on, but just remember this excitation frequency magnitude here. The angular frequency is calculated by simply taking the excitation frequency, multiplying by 2 pi, and we get 34.03 radians per second. And finally, we want to calculate the centrifugal force. So the centrifugal force is the angular frequency squared, multiplied by the eccentricity, converted to feet, multiplied by the mass of the rotor in slugs, and we get 1.56 kips. So we want to place these centrifugal forces initially as static loads on the structure, and we'll have 2 centrifugal forces, one acting in the horizontal direction, as we can see from this diagram on the right, and then we will apply an additional static load case to represent the centrifugal force in the vertical direction here. But it should be known that as these machines are rotating, we have a pi over 2 phase shift between that vertical and horizontal force. So they're not acting together, but rather we want to take into consideration that as this rotor is rotating here, that we're going to have 100% in the horizontal direction, but we'll continue with that pi over 2 phase shift to then see 100% acting in the vertical direction. Now, in order to apply the centrifugal force at these openings, we simply need to divide here by the total length of the members that make up this opening, and that's 33.6 feet. So we get a value here of 0.047 kips per foot that will be applied to the members. So this will make a little bit more sense when we go into our program RFEM to review the structure here. So as you'll notice, we have our industrial steel structure, and the cross sections are composed of W shapes. So we have a W8 by 35, we have W6 by 9, and then for our diagonal bracing here, we have W4 by 13. We do have a couple concrete platforms here. If we take a look at the thicknesses, these are going to be 4,000 PSI concrete, 6 inches thick. So we also have the loads defined. So within the dropdown at the top, I have 4 total load cases at this point in time. We have our dead load, which is automatically going to include self-weight, but notice here that I also have applied an area load. So we have 10 pounds per square foot applied to the structure at both levels. The area load applied over on the right-hand side was used with our load wizard so that we could correctly allocate this to the members based on a one-way area load distribution. So we can right-click to display separately to see those magnitudes here. Now, in addition to the basic dead load, we also have the dead load from the machine. So this is essentially just the force of the machine sitting on the structure, 0.08 kips per foot. Then going back to the PowerPoint, we have those 2 centrifugal force load cases. So we have load case number 3 here, which is that centrifugal force in the vertical direction. So notice this magnitude 0.047, which again just came directly from the PowerPoint. If we're curious to know the total length of these members around the opening, we can hold down our control key to select all of these members. You can right click, and under the center of gravity and information, we do see here the total length given to us as 33.6 feet for these selected items. So we have the centrifugal force in the vertical direction, and we also have the centrifugal force in the horizontal direction. So identical magnitude here of 0.047, but of course we want it to act in that horizontal position based on the global x-axis here on the structure. So now that we have reviewed the structure as well as the loads, what we would like to move forward with now is our dynamic analysis. And we activate these add-ons by right-clicking here on the model name within the navigator to access our base data. Alternatively, we can launch the base data directly here within our quick tools up at the top. So this is the dialog box that would be presented to us when we initially first create the model in RFEM, but we can always access it afterwards as well. Under the second tab here are all of our optional add-ons. So again, RFEM is responsible for the standard static analysis, but we want to activate our dynamic analyses add-ons. And for today, we'll go ahead and turn on the modal analysis and the time history analysis as well. So when I click OK, at first glance, it really doesn't appear that much has changed, but we want to move forward now with our modal analysis for this structure to determine what those natural frequencies are, mode shapes, and so on. So we're going to go into our load cases and combinations dialog box. And the initial step that I want to take is under the load combinations. We're going to create a new definition type here. And in order to carry out the modal analysis, I do need to convert my dead load forces into masses. And I would like to combine the dead load from the structure, so that includes the self-weight, but also that 10 pound per square foot area load, but also take into consideration by adding the dead load of the machines. So both of these will be considered, and we can also rename this one for our mass combination. So now that we have created this simple mass combination, we go back to our load cases here, and we're going to create a fifth load case. And we're going to give this one the name modal for modal analysis. So rather than carrying out a static analysis, we want to use our dropdown to select modal analysis. And this is available because I've activated this add-on within the base data dialog box. So here we have some additional settings that we would like to set for the modal analysis in particular. And we do have two default options here. So you could either modify these default options, or you could create your own definition type down here in the lower left corner. For today, I'm going to increase the number of modes to a total of 15 for my calculation. We'll carry out the eigenvalue problem according to the Lenko solver, and we're going to utilize a consistent mass matrix here, taking into consideration the mass in the translational X, Y, and Z directions, as well as rotational about the X, Y, and Z axes. Under the settings, this is just the program converting those forces to masses. So we're going to take all Z components of the load, convert them to masses. We do have the ability to neglect masses as well, but we will not make any modifications to that. We'll just leave that as default with no neglection for now. The import masses allows us to choose that mass combination that we have created, considering both the dead load of the structure and the dead load of the machine. So now that we have input in all of this information, we can run our calculation. So the program will quickly run through this modal analysis, calculating a total of 15 different mode shapes. And once the calculation is done, you'll notice that we get a fourth tab over here in our navigator where we can use our drop down here to select one of the 15 different mode shapes that we have solved for. And everything will sync up graphically here to show us our relevant shape. But also we have the same information available to us here in the drop down within the table. So we can select the modal analysis. And again, those 15 different mode shapes are going to be shown that we can cycle through graphically within the table format. Now for each of these mode shapes, we also see the relevant angular frequency, the natural frequency, and the natural period. So it's also important to take a look at the effective modal masses tab. So this tells us our mass participation for each one of these mode shapes, but also the total mass participation down here at the bottom for all 15 mode shapes combined. And we'd like to determine what are our dominant mode shapes for this modal analysis. So taking a look at mode shape number 1, we can see that this one has the most mass participation in the Y direction. So this is certainly a dominant mode in the Y direction. We take a look a bit further down, it looks like mode shape number 8 would be our dominant mode in the vertical direction or the Z direction. Pretty relatively low mass participation though in this direction of only 13%. And then finally, further down, mode shape number 15. So this is our dominant mode here in the X direction. We have a total mass participation of 90.87%. So keeping mode shape number 15 in mind, we go back to the natural frequencies tab, and what you'll see here is a natural frequency value of our structure of 5.388. So this is in Hertz, and if you remember back to the PowerPoint, I had mentioned to keep this value in mind, and you'll notice that these two magnitudes are very close together. So this should immediately tell us that we're inducing these excitations with an excitation frequency that's very similar to the structure itself, that we need to carry out a time history analysis. And ultimately, we're trying to avoid what we call resonance. So most of you are probably familiar with this term, but it's essentially a phenomenon that occurs when a structure is subjected to an external force or vibration. In our case today, it's these rotating machines that's of similar magnitude to its natural frequency. And this typically results in an amplification of the vibration. So going back to RFEM and knowing that these two frequencies coincide, we'll now move forward from the modal analysis to the time history analysis. So we'll begin with the time diagram. So going back to the first tab here of my navigator, you'll notice that we have a new folder available to us under dynamic loads. And this is only available because I've activated that time history analysis add-on. And we see here where we can create our first time diagram definition type. So we'll go ahead and click on this, and the dialog box opens where we can input either a user-defined time diagram, which you can see in table format. We can put in the time and we can put in the multiplier, essentially telling the program how this force is going to vary over time on the structure. Now, alternatively, we have the function option, which is what we'll be utilizing for this first example. We can go ahead and rename this time diagram if we would like as well. So I'll call this one vertical component, and the multiplier function would now be input as a sine function. So remember, we have these rotating machines, therefore we want to represent this as a sine function where we input in the sine of the angular frequency, which is 34.03 directly from our PowerPoint, and we multiply it by the time parameter. We'll go ahead and close these parentheses. We set the total time limit here to 10 seconds, which is just default. And we see our diagram populate visually at the bottom of this dialog box. We then want to make a copy of this time diagram, and we're going to rename this one to horizontal component. Very similar multiplier function here with the sine of the angular frequency, but if you also remember back to the PowerPoint that we have this pi over 2 phase shift that's occurring between the horizontal and the vertical force. Therefore, in order to account for this directly in the formula, we will add 1.57 to account for pi over 2. Again, 10 seconds is adequate. So if I hold down my control key and I zoom in here with my mouse wheel, we can see this diagram in a bit more detail. So for the horizontal component, you'll notice that at time equals 0, we essentially have 100% of that load acting on the structure. But as we move to a time duration around 0.04, we're going to have 0% of that horizontal load acting on the structure. Now, if we toggle to the vertical component, what we should see here is exactly opposite. At time equals 0, we have 0% of the vertical load. And at time equals 0.04, we have 100% of that load load acting on the structure. So this all just goes back to this simple diagram in the PowerPoint, trying to represent these centrifugal forces as a function of one another. That again, we have 100% of the force acting in the horizontal direction, but at a phase shift of pi over 2, we want to in turn change this so that 100% of the vertical load is acting on the structure. So these time diagrams just relate these static centrifugal forces to one another and how they're going to vary over time. So now that the time diagrams are available over here in our navigator, we want to go back to the load cases and combinations, where under the load combinations tab, we're going to create a new definition type here, and we can give this one a name of time history analysis. The analysis type is not static analysis, but rather time history analysis available in our dropdown. And very similar to the modal analysis, we just need to input in a few settings here. So we'll go into the default definition that's available to us, and notice that we have two options here for our analysis method, either the linear modal or the linear implicit newmark. So we will be moving forward with the linear modal for this first example. And this is certainly a more precise, quick, and recommended path forward for the analysis method if the structure has a low number of modes that have been calculated with the modal analysis add-on. This is also assuming that we have sufficient mass participation as well. But underneath the hood, that multi-degree of freedom system is going to be broken down into many single degree of freedom systems, and the solution of that decoupled system is then going to be calculated with the implicit newmark solver. Now, alternatively, if we choose here the linear implicit newmark solver, this is a direct time integration method where small time steps are needed for an accurate calculation. You should know, though, you do not need a modal analysis. So that's not required here, in contrast to the linear modal, where we always have to carry out that modal analysis, but linear implicit newmark, you do not. This is recommended for complex structures requiring a high number of modes in order to achieve that mass participation. So again, in our case today, we'll move forward with the linear modal. Now, the maximum time is the total time duration that I would like to consider for this time history analysis. And for our example today, we will choose 5 seconds. The save time step is the number of steps you would like to export out back into RFEM to view the results. So obviously we don't want to set this to something too small because it's just going to take the program a lot longer in order to populate all of those results. So we'll leave this as 0.01. Now, the split save time steps is further going to divide here the save time steps, but this is what's actually used in the calculation itself. So I'm going to further divide this by 10 so that technically with the actual calculation, I'm calculating every 0.001 seconds, but I'm only going to export out 0.01 seconds for my results. Now, additionally, you'll notice that we do have a damping tab, and for the modal analysis here, the linear modal analysis, we have both Lear's damping available where we can directly input here the damping constant, quite simple. We also have the Rayleigh damping where we would need to input the alpha and beta coefficients. Now, alternatively, just to show you, under the linear implicit newmark, you'll see here under damping that only Rayleigh is offered. So that is required for this calculation method, that alpha and beta. But we do have a function here in the program where we can automatically calculate from Lear's damping. So you'd want to determine from the natural frequency analysis, what are your two dominant nodes? And from these two dominant modes, what are the relevant natural frequencies? What's the Lear's damping constant you're trying to achieve? And then the program will automatically calculate both these alpha and beta coefficients. But going back to a linear modal, initially we're not going to put in any damping for our first calculation here. Okay, so once these settings are complete, we are going to import in the modal analysis because that is required for this solver. We only have one modal analysis that we have available in the model, so that's what's selected here in the dropdown. And finally, we need to relate those static loads. So if you remember, we have both load case 3 and load case 4 for those centrifugal forces in the vertical and horizontal direction acting at these openings. And we need to relate them to the time diagram. So how are these loads going to vary over time? And the first centrifugal force in the vertical direction is, of course, going to be related here to my time diagram in the vertical direction. But my centrifugal force in the horizontal, we want to set this to the time diagram in the horizontal direction as well. So now that we have set the static load cases to the relevant time diagram, we would like to run this calculation. Now we don't need to rerun the modal analysis. The program has already solved for this. Our results are saved here. And then we move on to the time history analysis, taking into consideration the full 5 seconds here of how these rotating machines will be directly applied to the structure. So once this is done solving, we are presented yet again with our results directly within our navigator over on the left for time history analysis, as well as in our table, we see time history analysis available here as well. So initially you'll notice that the program allows us to view, let's say, the global deformations of the structure based on the relevant time step. So currently at time step 0, nothing's going on with the structure here in terms of the deformation. But as we continue to cycle through these time steps, well, that's where we start to see the relevant deformed shape based on those centrifugal forces acting on the structure. And the same concept is available for other result information like our member internal forces. So for example, we can view the axial forces at this particular time step, or we can view bending moments, or perhaps we want to view the shear forces. Surface internal force information is available, and also support reactions. So we can turn those on again for this particular time step. And all this information is also available here in table format. So we can filter here to the results by the member, for example. And as we click through this table for the internal forces on the member, what else you'll notice is that the program syncs up automatically here to tell me exactly which member I'm looking at. And that red arrow is going to point to where the controlling internal force is that I'm currently viewing along the length of the member. So this is for each individual time step, but if we're rather interested in an envelope solution for the full 5-second duration, we can just simply turn off this checkbox. So now the program is going to give us our results here over the total time duration. So we can turn on, for example, the global deformations. And if we look graphically, we're seeing 2 deflected shapes here. And this is just simply because you'll notice under the envelope results that both the max and the min values are currently turned on. If we're interested in only the max deflection, we can toggle to this, maybe only the min deflection. Same concept for our member internal forces. So for example, if we take a look at max and min for our axial forces, you're going to see both of these values displayed on the member, but we could certainly toggle to any one of those other options. Now, all of this information shown graphically is certainly very helpful, as well as in table format, but I do want to go back to the navigator here to discuss the calculation diagram. So I'll go ahead and collapse some of these folders, and you'll notice the calculation diagrams is available here directly within the navigator list. And this is going to be highly used for any time history analysis. So this is going to give us more information about the structure's behavior over the total time duration. So under the first definition type here for my calculation diagram, we want to toggle this to a time history analysis. Now, the program is automatically going to display a diagram here based on the max deformation. But notice within this dropdown that we really have a lot of different options to choose from, including nodes for the global deformation, maybe want to view the accelerations on the nodes or member internal forces. So I'm going to start here with the global deformations of the nodes, and I'm going to pick this particular node up here at the opening where one of my machines is sitting. And currently the value shown here under this second dropdown is going to be the total deformation, considering all three directions, X, Y, and Z. But instead, I'm going to view the deformation in the X direction only. And when we take a look at this, we can clearly see that resonance is an issue, that this deformation in the X direction is just continuing to grow as time goes on. And likely if we were to expand the total time for a time history analysis, it would just continue to grow. We see here a value of 1.4 inches. So if we toggle instead to something like our acceleration on this node, and we want acceleration in the global X direction, again, the diagram looks very similar. So if we take a look at the total magnitude here of this acceleration at the end of the 5 seconds, it's 141 feet per second squared. So this is certainly not an acceptable value. And when we're interested in what are some of the recommended acceleration limits, there's plenty of resources out there. If we take a look at AISC Design Guide 11, for example, it really depends on what your structure is going to be used for. Something like an office is going to have a much lower tolerance value for acceleration versus something like a gym. But somewhere at the low end, it should be around 0.5% G, and somewhere at the higher end of acceptable tolerance values here is 5% to 10% G. But in any rate, we are far over that with this particular structure. So we need to make some modifications. And the first thing that I would suggest doing is to consider damping. So we'll go back to the load combination here and that time history analysis. We've already been within these settings before under the damping. So this time we want to consider using our dropdown, the Lear's damping constant. So for this particular steel structure, we'll go ahead and set this at 0.02. So we'll click OK. The program tells us we need to delete our results and rerun the calculation. Now, nothing changed with the modal analysis. We should see the same results there. But now with this time history analysis, we've introduced the damping matrix in consideration with the dynamic analysis. So we should see slightly different results here now that we're considering damping. So now that this is finished, we will immediately go back to that calculation diagram. So we can see it listed here in our navigator. We don't need to redefine it. It's already been saved. We're currently looking at the acceleration of node number 45 in the X direction, and our diagram certainly looks slightly different. We're not seeing maybe those accelerations growing linearly, but rather leveling off. If we take a look at the total magnitude of the acceleration, it is around 40.79 feet per second squared. So this is probably still an issue. The acceleration is far too high. So we need to continue to make additional modifications to this structure. Well, the obvious choice would be to change out some different cross sections here. Maybe we can modify the cross sections, which will in turn affect the stiffness, and our modal analysis may output different natural frequencies now that don't necessarily match the rotating machine. So we can do this directly with the cross sections listed. So for example, these diagonal braces, W4 by 13. We could simply double click and exchange out to a different W section. But the question might be, well, do we go with a cross section that is bigger? Do we go with a cross section that's smaller? And we could certainly trial and error and keep running through these different calculations. But I'd like to show you a different method, which is available under the Special Objects folder. It is called the Structure Modifications. And we can go ahead and double click to create our first structure modification where we activate the sections option. And we get a new tab here under sections with our 3 different W sections, including the W4 by 13 for those diagonal braces. And we have the ability to directly apply a factor to the cross-sectional area, which in turn is going to increase or decrease the stiffness of the axial stiffness of the member used in the calculations. So rather than exchanging out the cross-section, we can just more or less play around with the stiffness properties directly to see how our structure is affected. So under the W4/13, the first thing I want to do actually here is to give it a name. We'll call this one double stiffness, and the area factor will be set to 2.0. The area in the Y is also set to 2.0, and area in the Z is 2.0. So again, just increasing the stiffness twice the amount here. Now we're going to make a copy of this structure modification, and we'll call this one half stiffness. So in this scenario, what we want to do is to, instead of applying a factor of 2.0, we'll apply a factor of 0.5, just to again see how the structure responds to maybe a smaller cross section without actually swapping out those cross sections quite yet. So now that we have these structure modifications shown here, we can go back into our load cases and combinations. Under the load cases, remember we have our modal analysis with no structure modification sets, just originally the results that we have already looked at. But I'm going to make a copy here, and I'm going to call this one double for double stiffness. Under the structure modification, we can turn on that definition for double stiffness that we just created. Again, where we're going to increase the axial stiffness times 2 for these diagonal braces. I'm going to make an additional copy here, and we're going to rename this copy half so that we can activate here half the stiffness for the diagonal braces. Well, it's not just enough to do it for the modal analysis, but we also need to apply this to the time history analysis. So again, I can simply create a copy here, and with our original time history analysis, we will first rename it, but notice that with the linear modal, we can now import in the modal analysis where we have increased the stiffness by 2. The program automatically detects that we also want to apply this structure modification to the time history analysis, because remember we have these static load cases that vary over time. So we need to also apply that stiffness modification to this scenario here. And we make an additional copy, and in a similar manner, we call this one half, and we're going to import in the modal analysis with half the stiffness set. And then you can see here the structure modification half stiffness is also set for the time history analysis. Okay, so now that these are run with the relevant stiffness properties or modifications set, we can just go ahead and click calculate all. So this is going to cycle through first my load cases here, which is fine. We're not really concerned with them. But then you'll also notice that the program is going to go ahead and calculate both of those modal analysis with the stiffness modification set, and then we're now running through both time history analyses with the additional stiffness modifications. So the first thing that I'll go to now that the calculation is done is those calculation diagrams. So we'll go ahead and double click on here, and we see the same calculation diagram, but that's fine because we're still referencing that original time history analysis with the same cross sections, same stiffness, nothing changed. We make a copy of this, and this time we want to reference the time history analysis with the double stiffness. And now we see that our acceleration of that node in the x direction looks quite different. No longer do we see that acceleration growing, but rather it remains pretty constant over the 5-second duration. And if we take a look at the total magnitude of the acceleration, it's now around 0.4 feet per second squared. So this is much better and well within those tolerance values. Perhaps we make an additional copy here to select half the stiffness. Again, resonance is no longer an issue. So we don't necessarily always have to increase the cross-section size. Even decreasing a cross-section size may allow you to overcome issues like resonance. However, we do need to still take a look at the total acceleration values, a little bit higher here, around 4 to 5 feet per second squared. So it'd be up to you as an engineer to determine, okay, is this within the allowable range, or do we need to make further modifications? But once we have an idea about the general stiffness options based on those factors, then we can go in and make modifications to that W shape. Okay, so that will conclude our first example today with these induced vibrations on the structure. We now want to turn to our second example. So we'll go back to the PowerPoint here, and this is going to be blast analysis. So with the blast analysis, we certainly can utilize the same add-ons, a time history analysis add-on, to replicate a blast analysis on a structure. So very simple example for today. You can see it outlined here with the reference given at the bottom of this slide, that we have some type of cylindrical structure. So this is the plan view of that cylindrical structure. Perhaps we have an explosion somewhere in the exterior here. Therefore, we have this incoming pressure wave. And you'll notice that based on this reference, the incoming pressure wave, the magnitude of this pressure varies as we move around the perimeter of the structure. So ultimately, we want to replicate this in RFEM, and we do so with what we call a free load varying along the perimeter. And here's just a couple screenshots that we will visit in just a minute within the RFEM model itself, but we do have the ability here to replicate this loading. Now, when we talk about blast analysis, it's quite common to represent the blast as a triangular shaped development of load versus time. And that's what you'll see here at the bottom of the page, that over a very short duration of time, 0.15 seconds, we're going to see that load increase linearly to 100% for the pressure wave, and then in an equal manner, it's going to dissipate quite quickly at 0.3 seconds total. So we also want to replicate this with a user-defined time diagram. So you can see that triangular shape shown over here on the right-hand side. So let us go into the RFEM model directly, where we'll go ahead and toggle to this open model here. So you'll notice that for this very simple example today, we have a 32-foot high cylindrical structure, 33 feet in diameter. Really consists of a single surface here. And if we take a look at the thicknesses, it's going to be A36 material, 2 inches thick. Also, we have a pin support down here at the bottom that is applied as a line support. We also have the loading applied. So we have 2 simple load cases for this example. We have the self-weight, which no additional loads are applied to the structure, just internally that self-weight is considered within this load case automatically. But then we also have that blast load. So this comes from the PowerPoint and the reference mentioned, where we wanted to vary this load around the perimeter. And we take advantage here of what we call a new free rectangular load. So with the free rectangular load, if I go ahead and double click on the options here, you'll notice that the load distribution can be set to varying along perimeter. And I also wanted the load to act normal to the face of the surface. So this is based on the local z-axis of the surface itself. We also need to input in here a reference load magnitude, so -10 kibs per square foot. So taking a look now at the second tab that is available, we see in table format where we can input in degrees. So this first column, 0 degrees, 30 degrees, 60 degrees, and so on. We can also input the relevant factor. So again, this just comes from the PowerPoint, and then the program will automatically take this load magnitude here and the parameters set in this table to calculate the total load acting on the structure and how it should vary, again, as we kind of move around the perimeter. So that's a little bit about just the basic static load that is applied here as a general load case. Now, we want to define that time diagram. So I will go into my navigator over on the left in the dynamic loads folder, where very similar to the last example, we just double click here the time diagram. And this time, instead of using the function, we want to set this to user defined. And for a very simple application today, at time equals 0, we want a multiplier of 0. At time equals 0.15, again, just referencing the PowerPoint, we want the multiplier to be 1. And then finally, at time 0.3, we would like the multiplier to be 0. So we see this triangular shape displayed here that will be used to tell the program how this static pressure load that's shown here in the background is going to vary over time. So a very quick impulse, so to speak. So we have this single time diagram defined. So we click OK, we see that listed over here in our navigator. And we want to go into the load cases and combinations. So I will preface that for this particular time history analysis, I'm going to run a linear implicit Newmark solver. So this is in contrast to the linear modal solver. What this means is that I don't need to run a modal analysis. So everything that we saw in the first example, that modal analysis was required because we were running the modal solver. And unless we're interested in determining what the structure's natural frequencies are, periods, mode shapes, and so on, we really don't need to run the modal analysis calculation here in the load cases for a linear implicit Newmark solver. So immediately we jump to the load combinations instead. We create our first definition type here. And the load combination name can be set. We will call this one BLAST time history analysis. You'll see here that the analysis type is set to time history analysis rather than static. And very similar to our last example, we have our settings. Now, the type of analysis method here is set to linear implicit Newmark. The total maximum time is going to be 1 second. So typically with a BLAST analysis, we don't need to carry out the time history analysis over a long duration of time just because that load impulse is so quick. So 1 second should be adequate here. The save time step will be set at 0.01. And then we further want to split the save time step here by 10. So remember that this is the value that's actually used here within the calculation. So we'll technically be using 0.001 for this linear implicit Newmark calculation, but we're going to export out every 0.01 seconds into RFEM to view those results graphically. Under the calculation parameters, so because we are not running that modal analysis, you'll also see here just some additional settings specific to the mass matrix for the linear Newmark solver. The type of mass matrix will be set to consistent, for example, acting in the translation directions as well as rotation about those global axes. And then we also have the same mass conversion type, similar to what we saw in the modal analysis in example 1. And finally, we have the damping. So for this example, I'm not going to consider damping, but it's worth pointing out again, remember that with the Newmark solver, we only have the ability to define Rayleigh, or we can allow the program to convert from Lear's damping. Again, we'll leave all of these values as 0. So we need to import in the masses from either a load case or a load combination. We don't have any mass combinations that we created for this example. Rather, I'm just going to import in the masses from self-weight alone, and that's available within this first load case. And finally, we have the assignment tab where we take this BLAST load, and we can see it displayed on the structure here as a standard static load, and we relate this to the user-defined time diagram, and that was that triangular development of load versus time, which is automatically set here because we only have one time diagram defined now in the model. Okay, so now that these are set and correlated, again, how this pressure is going to vary over time, we are going to run the calculation. It should be known that we're not running through the modal analysis, but rather directly to that time history analysis. With the Newmark solver, it does take just a little bit longer. And I had mentioned that when we were talking about the modal solver, it is a bit quicker, it's more precise, but can only be used when we have adequate mass participation and we're carrying out that modal analysis with relatively low number of mode shapes. But regardless, we'll carry out the time history analysis here for the full 1 second duration. And once those results are done solving, we see them presented here back in RFEM. So we'll go ahead and turn off the display of our loads. So you'll notice initially we have the time history analysis available in the navigator, same concept for the table, just like what we saw in example 1. And if we toggle to the time duration of 0 seconds, as we would expect, that pressure wave has not been applied to the structure yet. But if we cycle down here and choose time equals 0.15 seconds, this should be the highest global deformation of the structure because that's 100% of that pressure wave being applied. And then as we cycle through these additional time steps further out, we're going to see that deformation slowly decrease because we're going to apply less and less of that pressure on the structure. We also can view information, if we maybe back up here to 0.15 seconds, such as the surface stresses. So we can activate here the stresses. Maybe we're interested in the von Mises stresses. So we find that under the equivalent stresses here, we can activate von Mises, and we can go ahead and see this graphically within the structure. Now, this is all for this particular time step. So again, keep in mind if you're interested in an envelope solution, let's say showing the maximum von Mises stresses, we would just need to simply turn off this checkbox. This is going to show us, based on what we have set here under the envelope value, either the max or the min von Mises stresses over the full 1 second duration. So again, we want to turn back to our initial navigator here to access our calculation diagrams. So we'll go ahead and create a new calculation diagram here, and we're going to activate the time history analysis. We only have one time history analysis under the load combinations available. Notice that the program automatically defaults here to this first option, showing us the maximum deformation of the entire structure over that 1 second time period. And exactly as we would expect, what we see here is the max deformation around time 0.15 seconds until that load dissipates based on the time diagram that we have defined. We also can take a look at here, instead of necessarily just, not necessarily just the global deformations of the structure, but we can choose, again, specific nodes to view those global deformations, accelerations, and so on. But we can also activate here, perhaps we want to leave this diagram, we can create a copy and we'll choose the surfaces von Mises stresses. So we see this option within our drop-down box here, and we select the relevant von Mises stress. We do need to either graphically select the surface, which we can do here, or we can type it in, and then we would graphically select the node that we're interested in. So maybe I choose one of the nodes I generated down here at the bottom of the structure. Then we can see the relevant von Mises stresses and how these vary over the total time period as well. Again, as expected, the shape matches quite well with our time diagram where we see the total von Mises, and currently we're looking at strains. Let me back up here and go to stresses instead. The von Mises stress here is set at 24.4 at around that time period of 0.15, as we'd expect, with the highest load applied to the structure. Okay, so that should give us just a very quick example of a blast analysis and how we can also utilize the time history analysis add-ons. The final thing that I just want to quickly point out is we might be wondering, how do we combine the results of our time history analysis with additional load cases or additional load combinations? So you'll notice back under the base data, first of all, to begin with, I haven't generated any load combinations automatically to the standard, but you could certainly turn this on here with this checkbox and select the ASCE 7 or the NBC. For today, everything was code independent, but what I did turn on was the result combinations, and we get this additional tab here, and we can also activate what we call sub-results. So now with the result combination, I create a new definition type, and this allows me to combine any load case, load combination with those dynamic analysis results. So for example, if I wanted to combine self-weight with the time history analysis from the blast, we can go ahead and do so by moving both of those over here on the right. Now, it should be known that these are linearly combined because we take the results from load combination 1, we add them to the results of this, of load case 1, and we add them to the results of this time history analysis. So everything is done linearly. The load type can be set here to permanent. So if we always want self-weight acting, same concept for the time history analysis. Transient just means is it alternatively acting in order to give us, the worst case scenario or envelope solution here. The sub-results option that we checked under the base tab here allows me to choose a particular time step. So for example, if I choose time step number 16, these results will then be combined with self-weight. Alternatively, if I'm interested in an envelope solution, I could choose this option all. So that way the envelope results of the max and min are combined with the self-weight. We can create multiple result combinations here, combining different time steps. We can rerun these calculations down here at the lower right-hand corner, and then we can view our results just like what we've seen up until this point. Okay, so we will go ahead and conclude today's webinar. This presentation was recorded. It will be placed on the same web page, usually within the next day or two that you registered for the GoToWebinar. And I have already placed the example models on that web page as well, so you can download them. And if you're currently not utilizing RFEM, I would certainly encourage you to download the free 90-day trial version that you can find on our website, deluval.com. So the trial is full capability and includes all add-ons, including the dynamic analysis add-ons that you saw today. You can open up the structures that I used in the example and then follow that recording again, step by step at your own pace if you prefer. If you have any questions about today's presentation or anything else, feel free to contact us with our contact info shown here at the bottom of the page. Our phone number to our Philadelphia office is 267-702-2815, and our email is info-us@delubal.com. So we will have more upcoming webinars that will resume in January 2024. You can register at delubal.com under support and learning webinars. As most of you know, I tend to send out a reminder email before these take place. So just keep an eye out for that next month when that next webinar will occur. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So this is a requirement of the states that we are pre-approved providers that you are here for the full 60-minute duration in order to receive that PDH. If you did watch with a colleague or you watched in a conference type setting and you yourself did not register with your own name and your own email, but you were here for the full duration and you're wanting that PDH, just go ahead and request that to the email address shown here, info-us@delubal.com. Let us know who you watched it with, and we'll be happy to provide that PDH to you. And with that said, I want to thank everyone for attending. And as always, we hope to see you at our next webinar. Thank you.